Dear students, now we will discuss about the derivations of strength of material. First part, we will discuss about the first part of strength of material, important derivations. First one is deformations of a body due to self-weight. This is important derivations. Actually, in strength of material, university question papers, they will ask, particularly in the university question paper, they will ask, it is a problematic papers. One problem, the rest of the portions will be derivations. Only two parts they will ask in the big questions, part B and part C. Either derivations or problems. So we will see the first derivations. Deformations of a body due to self-weight. Consider a bar AB hanging freely under the own weight as shown in figure. Length of the bar is L, cross-section area A, Young's modulus E. Then specific weight of the bar, unit length W. Now consider small sections dx at a distance x from B. So the weight of the bar for a length x will be P equal to W A into x. W is the specific weight, A is area of cross section, and a distance x. Generally, the elongations of the any sections, the formula will be PL by A. Load, length, area of cross section into Young's modulus. In this case, P, load is the self-weight. No? From here only, because we are considering this sections only, from here the load will be W A X. And L, length of the bar, is only small section only, no? So dx. AE. So AE cancel, it becomes WX dx by E. Total elongation of the bar may be founded by integrating these equations. We will get total elongation. So that limit is 0 to L. 0 to L Wx dx by E. W by E is the constant we take outside. That variable is x dx. Integral 0 to L. After integrating, we will get x square by 2. While substituting the limits, it becomes W L square by 2E. Then W is the specific weight for unit length. Suppose if it is whole length, means it becomes weight of the bar. So WL equal to capital W. Then this equation becomes WL by 2A. Then stresses in the bar, second derivations, stresses in the bar of uniformly tapering circular sections. In this case, so this is the tapered part, circular part. So this diameter is D1, this diameter is D2. Okay, this is uniformly tapering cross sections. Then consider a circular bar AB of uniformly tapering circular sections as shown in this figure. P is the pull on the bar, that is load. L is the length of the bar. D1 diameter of the bigger end, D2 is the diameter of the smaller end. Now consider a small element dx at a distance x from A. Okay, small x from A, dx we are taking the small element dx only, thickness dx only. So in this case, what about the diameter of the section? This diameter may be found out by D1 minus of D1 minus D2 into x by L. This distance by whole distance. For simplifying the calculations, D1 minus D2 by L we take as K. This one is K. So that this is the diameter. The cross-section area of the section means pi by 4 diameters, pi by 4 d square. Okay, pi by 4 d1 minus kx whole square. Because that the element diameter is d1 minus kx. So that's square. Then strain equal to stress by modulus. Stress means load by area. Load P, area this one. This 4 is denominator to denominator, hence it becomes numerator. So 4p by pi d1 minus kx whole square by E. Further simplifying, we will get 4p by pi d1 minus kx whole square E. Then total extensions of the bar. So maybe get by integrations. Limits is 0 to L. 4p dx by d1 minus kx whole square E. 4p by E take outside because it is a constant. Dx by d1 minus kx whole square. Then this should be integrated. So this is taken for numerator. Numerator by power becomes minus 2. Thereafter integration. Minus 2 plus 1 becomes minus 1 by minus 1. Then coefficient of x minus k. Then applying limits. So we will get 4p by pi ek 1 by d1 minus kl minus of 1 by d1. Then substituting k equal to d1 minus d2 by l, in this case, in both the cases, and simplifying, we are getting 4pl by pi e d1 d2. This is the elongations of the taper sections. Then relations between bulk, third case, relations between bulk modulus and Young's modulus. In this case, this is the ABCD. This one ABCD A dash A1 B1 C1 D1. So it is a cubic sections. Then sigma is the stress, L is the length of the cube, E Young's modulus. Now let us consider this load is applying, that forces, I mean stress is applying mutually perpendicular to each other. The tensile strain equal to, strain means stress by modulus. Tensile strain equal to sigma by E due to stresses on the face, this face, B, B1, C1, C and opposite face. Then this is the tensile strain. When it is tensile strain means, what about this case? Actually stress is tensile, but in this case A1, B1, C1, that surface will be compressed because of this tensile nature. This surface will be compressed. So compressive lateral strain equal to, so due to stresses equal to face on the face A1, B1, opposite D1, D1, C1, C. And other case, in this case also. Compressive, in this case also lateral strain equal to, compressive lateral strain equal to 1 by m sigma by E due to stresses A, B, C, D and A1, B1, C1, D1. Therefore, net tensile strain delta L by L equal to sigma by E minus of 1 by m sigma by E minus of 1 by m sigma, simplifying sigma by E 1 minus 2 by m, equations 1. The volume of the cube, because we are taking the side is length L, so that it becomes L cube. Then differentiating these equations with respect to L, dV equal to dV by dl equal to 3L square. dV by dl equal to 3L square. We want dV 3L square into sigma L. Substituting the value of delta L by L in first equations, delta V equal to 3L cube into sigma E by E 1 minus 2 by M. So in the place of delta L by L, we substitute sigma by E 1 minus 2 by M. Further, delta V by V substituting, because in both sides LH and RHS we are dividing volume V, both sides, this side also, this side also. So delta V by V, in this case V V formula is L cube. We are substituting L cube here right side. So L cube cancel. And simplify, we are getting 3 sigma E 1 minus 2 by m. Then in this case, stress by volumetric strain equal to bulk modulus. So that we want sigma by volumetric strain. So in this case, sigma here, we divide here and it becomes left side means E by 3 1 by 1 minus 2 by m. Then this simplifying, we are getting me by 3 m minus 2. This becomes K because stress by volumetric strain equal to bulk modulus. And the next case, bending stress. In bending stress, this is the cross-sectional bar. So cross-sectional bar, while bending, this is RS is the neutral axis. Even after bending, so this RS will not be changed. Then BD will be tensile elongated and AC will be contractions. So AC is contractions and BD will be elongations, RS will not be changed while this bar is bended to a radius of R. Then PQ will be changed, RS will not be changed. After bending, this bar becomes A dash, C becomes C dash, B becomes B dash, D becomes D dash. Then RS is R dash and S dash, but RS value will not be changed. RS equal to R dash S dash. And the P dash S dash we little bit extended, elongated. Then on neutral axis, that the bending stress will be 0. At the surface only, bending stress will be maximum. Now, after bending, that PQ will be elongated. So delta L equal to PQ minus P dash Q dash. Or P dash Q dash minus of PQ, whatever may be. Then strain equal to delta L by original length. Then PQ minus of P dash Q dash. Why this PQ means? So the top portions is contraction. So that PQ is greater than that of the P dash Q dash. So that PQ minus of P dash Q dash. Then PQ minus P dash Q dash by PQ. From the geometry of the curved beam, in this case, then this one, O, this is R, O, O, S dash or RS, the distance is R. Then PQ distance will be, because this distance is Y only, no? So that R minus Y, PQ radius is R minus 1. P dash Q dash by R dash S dash equal to R minus Y by R. Then subtract, so this has to be subtracted from 1, both sides, 1 minus of this one, 1 minus of this one. Simplifying, R dash S dash minus P dash Q dash by PQ, this becomes Y by R. This R dash S dash will be PQ, because in normal sections that PQ and RS all are same only, so that PQ minus P dash Q dash by P, that is equal to Y by R. Then this is, what about this is delta L by L is strain equal to Y by R. Further, bending stress equal to strain into elasticity. Why? Elasticity equal to stress by strain, stress equal to strain into elasticity. Strain equal to Y by R, this is E. So Y into E by R. This equations becomes sigma B by Y equal to ER. Thank you.